Welcome everybody to the second StreamInsight talk today. My name is Roman. I'm the program manager in StreamInsight team in Redmond, and I'm here together with our architect Besim, who will co-present with me. Again, this is the second talk today about StreamInsight. This is a level 400 talk, and the preliminary talk was given by Thorsten this morning at 10 a.m. This was a level 200 talk, and I will not go into a lot of details regarding the big picture, regarding the main concept. So we considered this first talk today as kind of the preliminary to understand this level 400 talk better. If you did not see the introductory talk, I strongly advise you to later download the video and watch the video because I can't go into a lot of details about business aspects and concepts that Thorsten was presenting this morning. Okay, so what do we want to do in this talk? First, I'd like to talk about two sample use cases, two real-world use cases, and the challenges that came up in those and other scenarios regarding complex event processing. I'll then talk a little bit about writing queries using temporal windows, how to implement adapters, show a little bit of adapter code. We will then talk about the architecture. Besim will give you an overview on StreamInsight's architecture. And the extensibility interface, and we will then conclude with a demonstration of our event flow debugger tool. Okay, so very quick overview for those of you who have not been in the first session today. When we talk about CEP, the important thing that we always want to make clear is the paradigm shift between classical relational databases and complex event processing. In classical databases, you have static data and you have ad hoc queries. You fire your queries at your static data, whereas in event-driven applications, the data is the transient entity, whereas the queries are static. The queries are standing and the data flows by the queries. And what you want is an event-triggered, an event-driven processing of the data and not a user-driven processing. And that comes with implications. You have performance implications regarding latency and throughput. Of course, latency is, the desired latency is supposed to be small as possible, whereas the throughput is supposed to be as high as possible. And again, it's an event-driven paradigm as opposed to the query-driven paradigm. Again, a quick overview on the StreamInsight platform. If you download our MSI and if you install it, what you get is basically an SDK. You get a bunch of DLLs, and you fire up Visual Studio, you write a CP application against our DLLs. Writing a CP application, first of all, means to write input adapters. Input adapters translate your proprietary event format, your event source, into the canonical StreamInsight event format, so that it can be enqueued into the standing queries, which apply the desired query logic on that input stream, producing some output, which will then be picked up by the output adapters that were again written against the StreamInsight API, and producing some desired output on the stream end side. Could be persisting it into database, writing into disk, visualizing it, writing it into a web service, anything on the output side. Okay, first real-world use case. You might have seen this slide in Scott Guthrie's talk yesterday, talking about Silverlight. This is NBC Sunday Night Football. It's a rich Silverlight client application for viewing Sunday's football in a very flexible user interface where you can switch camera angles, you can replay, you can basically put together your own football program. So there are a lot of user events happening on the client side. All those events get streamed to the server, and StreamInsight is used to analyze and monitor those events. This is happening in the following way. The client data is collected on the server side, and all that telemetry data is then picked up by a StreamInsight input adapter, which streams the data into multiple queries. So what we are looking at are, for instance, queries that correlate geographical data, that correlate the user data consisting of an IP address with geographical data, enriching the data type by geographical data, Could be aggregations over time, counting the total number of events that came from the Silverlight clients, counting the session starts, when did people actually go online and start watching the program, counting the current active sessions. All that data is produced by the standing StreamInsight queries in real time and is then streamed into different output adapters, partly into SQL adapters, writing that pre-processed, scrubbed data into a SQL database, from where it is further processed into SSAS and reporting services, and on the other side also through a perf counter adapter into perf counters, so that you can use we can use Performance Monitor to watch those trends, to watch those queries in real time. Different example, this is something we did in collaboration with our manufacturing partner, OSIsoft, power consumption in data centers. It's all about reducing power consumption, monitoring power consumption on a fine-grained level. You can do that on the level of racks, maybe even machines, but why not try to monitor power consumption on a process level to find out which applications consume how much power? To do that, we did this little proof of concept, which has a two-staged approach to do that kind of processing. First of all, we are collecting the necessary data from the actual machines. This is, on the one hand, it's power consumption data that could come from a power meter and is then streamed as CP events through a power meter input adapter into a StreamInsight query. For the process data, that's coming from the event tracing for Windows framework, the ETW framework, picking up data like context switches, thread IDs, process names, and so on. All that data is processed by a StreamInsight query so that we get the reduced data rate with just important information containing CPU cycles per process ID. That data, that pre-processed data, is then streamed into a central historian, a time series archive, and that could be on a different machine, where we have the second stage of the query processing, where we want to correlate that data, that pre-processed data. And in this case, we correlate the CPU consumption of each process with the overall power consumption of that machine to have some rough approximation of the power consumption of each process, using then OSIsoft's visualizing tools to monitor that data. So that was a nice proof of concept of a two-staged approach. You have the event processing close to the edge, scrubbing the input data, reducing the data rate, writing that into a historian, into a time series database, and then use a second stage query to do some more complex aggregations and correlations. Okay, so in those two and many other use cases, many other scenarios, we are finding the same challenges. I want to detect interesting patterns over my input stream. I would like to reason about the temporal semantics, the temporal properties of my events. I would like to correlate data as well as aggregate data over time. And I want to do that without writing custom imperative code, without writing my own procedural code. What I need is a runtime environment for that kind of event-driven processing. So basically, what I need as a developer for complex event processing is a platform that takes care of all the heavy lifting and enables me to specify such solutions in a declarative way. Okay, so let's start with the query expressiveness. The query language that we provide, you have seen that in the introductory talk, is LINQ, which is closely related to SQL as a relational query language. So we have the same operators as you also have in SQL: filtering events, selection of events, calculations on the payload of events through project operations, joining multiple streams into one correlating stream data, partitioning stream data by our group and apply operation, taking one specific payload property and using that to create multiple partitions, and then apply some operation on each partition separately. Do aggregations over event windows, over windows in time, such as sum, count, average, min, max. And rank over event windows, again, over temporal windows. That's the typical top K operation that you also have in SQL. So let's have a look at some concrete examples here. What you see here is a link statement. It uses the object input stream, which I created through our API, which basically represents the event source. It's the collection of events coming out of my input adapter in a concrete query. Projection is a simple stateless operation that just applies an expression on the payload of my event. In this case, I divide something by 10, I create a new payload, and I have a one-to-one mapping from input and output of this operator. Filter just adds a where clause. It reduces the events. The events that do not fulfill the filter predicates will be dropped by the operator. In a join, I look at a specific join predicate, a join condition, correlating the events by the explicit join predicate that was specified by the query, together with the implicit join predicate, which is the temporal overlapping. If events overlap temporally and fulfill the join condition, they will be output by the join operator, otherwise they do not join. Now, with aggregation, it becomes more interesting because this is where we leave the traditional link syntax. This is where we added extension methods to accommodate for temporal semantics. If you define an aggregation, you always define it over a window of time. So in this case, we apply a window on that input stream object. Here it's a tumbling window, and in a second I will explain more about that type of window. The window has specific size, and this means that over all events that fall into that window, I want to compute my aggregation. In this case, it's an average. So that will produce one output for each 10-second window, one event. Now I can do the same operation, but on my partition stream. Say I have, in this case, where I talked about the power meter example, I would like to aggregate and average for each of my power meter separately and not over all of them. So I would partition my stream by the power meters that are streamed into my query. Say they have a field ID. So I would group the stream by ID and then apply the aggregation, the windowed aggregation, on each of those partitions separately. Again, a very typical streaming pattern. First, I group something, and then I apply an operation on each group separately. And this is still plain link. Apart from the tumbling window operator, the group by and everything else that you see here is plain link. So let's have a look at the time windows. I mentioned the tumbling window in that example before. What does it mean to apply a time window on a stream of events? Let's assume a simple example. I have, over my timeline, I have a couple of point events here. Now, the simplest possible window is the so-called tumbling window, which has a specific size and just repeats itself over time. It starts whenever the old window ends. This means that every event falls into one specific window. Now, I apply an aggregation on top of that. Every window will produce one aggregation result. As an alternative, I might want to change the data rate. I might want to apply a window of, say, 1 minute, but calculate the output of that window every 10 seconds. So I need windows that overlap in time, that have a hop size which is not equal to the window size, which could result into events falling into multiple windows, like that. That's what we call a hopping window. Again, an aggregation on top of that will produce one output event for each incoming window, based on the events that are member in that window. Okay, time for the demo. So what I have here is a simple demonstration of, going back to the power consumption, I have a power meter which I use to plug my laptop in. So it's monitoring the power consumption of my laptop. And what it also does is it's providing its readings through a USB interface. So what we have done is we have an input adapter written against that power meter that is able to stream the reading events into a query. And on the output side, I have a little dashboard window that just displays the resulting events on my screen. Okay. So this is a very simple application. Uses the power meter input adapter to instantiate such an input stream, and then uses the input stream to write a query against that. And this is the simplest query possible that I also had on the previous slide. It's a simple project operation, no filter, no stateful operation. So what you see is the result of that query is basically a pass-through query. Let's keep the last 20 events. And you see the behavior of this input adapter. The input adapter reads events, power readings as fast as possible. And this is how this specific device behaves. It produces, if we freeze the output for a second, it produces maybe 50, 60 events per second. And the events have an ID and a wattage reading. Now, if we look at the query again, there's nothing special happening here. The only thing I do is I divide the input payload int w by 10. This is because this meter device delivers its readings in a fixed point integer value in tenths of watts. So what I need to do is divide by 10 and convert it into a double. And then I get exactly the current power consumption. Now, let's say I would like to reduce the data rate. I would like to have one output value per second, which should represent the aggregation over this 1 second over all readings that are received from the meter. So instead of taking each event separately, I apply a window. In this case, I take a tumbling window. And you've seen how IntelliSense helps me applying operators on top of streams. I see all the possible operators that our extension methods provide to the link query author. And in this case, I chose the tumbling window. Now, it takes a single parameter, which is the time span of its size. So I specify 1 second here. I do not need the ID, but now I need an average, which is based on the window. And you see that IntelliSense again gives you all the possible aggregations on top of windows. So I have average, count, max, min, sum. In this case, I am choosing average on top of the same value that I output before. So what you will see is that the event rate changed. I get exactly 1 event per second, and it's representing the average over the whole second of the received events. Now let's do something more complex. And I will cheat a little bit because I don't want you watching me type. Okay. So I have a more complex query consisting of 3 link statements. What I'm doing here is I'm still using average, but I'm computing 2 averages in parallel. First, I'm producing what I call a slow average stream, which computes the average over a window of size 3 seconds, but it uses a hopping window. It applies that window every 200 milliseconds. So it's a window that overlaps in time. It's 3 seconds wide, but it's applied every 200 milliseconds, and it's computing the average. At the same time, on my input stream again, I'm specifying a fast average stream, which does the same thing but has a smaller window. It computes with the same frequency as the other one, but it has a smaller window. I take the 2 windows and join them in a cross-join. In a cross-join in link, I don't need the second join clause with a join predicate. I just use 2 from clauses because I want to join every event on one side with the other side. And I'm applying some temporal shifting here to make sure that my events are overlapping in the way I want it to. And then what I compute here is what I call trend, which is the average of the fast stream with the average of the slow stream, which will give me some kind of a derivation of a slope, because I'm comparing the fast stream, the younger average, with the older average, so that I can see is my reading series of readings going up or going down. So now you will see if the two averages are equal, I will get exactly 1. This means my readings are not changing. Now, if I do something that uses up CPU power, I have a little app that eats CPU. You see, it goes up now because the short-term average is increasing, the long-term average is still behind. After some time, I'm now at 50 watts, it's still constant. It's a constant again. If I go to sleep, now it goes down to 35. My trend goes down for a second, now it goes back to 1. So it's a very nice example to declaratively specify a moving average, a comparison of two moving averages with 3 relatively simple link statements. Good. Any questions so far about that?
Could you show what that shift event time is?
Yes, yes. So what I do is actually I apply two temporal operations here. What my average does is it produces an output that is exactly corresponding to the window size. So the 3-second average will produce 3-second long interval events which will overlap. What I want to join are event streams that have a signal shape that do not overlap. So I need to take the average result and need to modify it so that the aggregation results do not overlap in the same stream. That means that, first of all, I shift the slow average stream by 3 seconds into the future because I want to look back, right? I want to say at each point in time what was my last trend from this point of view. So I move both of them into the future, respectively with their window size, and then I change their duration back to 200 milliseconds because that was my hop size. Now that will give me 2 streams of non-overlapping events, always looking back from the same point of time.
So where do you host this StreamInsight engine in this Forms application or in that console?
In that console application. We are following the implicit server here. So all I do is, it's literally 1 page of code here. All I do is I create my input stream based on the input adapter factory, and I'll show the factory code later on. I specify my query on top of that stream, and eventually I call the toQuery API call here to generate a query, which at some point I will start. And that will implicitly create the StreamInsight server, instantiate all the necessary items, and register the metadata, and start up the query.
So, and from that moment on, the events are flowing into the
Right.
adapter.
So what I do here in that specific application is my dashboard has a .NET event signal handler. As soon as I close that, I receive that shutdown signal in my main thread here, and I close my application.
And later on, you'll actually see a graphical depiction of the event flow in a
Yes.
debugger.
Right. So that's the control flow. The event flow is separate. And that's my application, right? Okay. So talking about adapters, moving from the logical query specifications to the physical properties of event streams. Adapters import data into the StreamInsight platform. There are several dimensions for adapter features and properties. First of all, adapters can be pull or push adapters. In a pull adapter, the adapter controls how often it retrieves event data from a specific event source, versus in the push model, there is some kind of callback functionality where the adapter provides a callback to the event source, which then asynchronously pushes events into the adapter. That's the most desirable and the most performant model. If you're able to provide such a callback and let the event source basically push the events into the engine. So we provide the adapter API to write adapters, but we also provide the observable model, which is basically modeling the reactive frameworks iObservable functionality in StreamInsight. It wraps the adapter framework and lets you specify event sources purely in plain .NET objects like IEnumerables, treating IEnumerables as event sources, and avoiding to write an adapter against our adapter API framework. So it's a nice, clean model. If you don't need the total control over event issuing behavior, if you can model your event source as an IEnumerable, you can basically instantiate such an event source within 1 or 2 lines of code and then write your query against that. So to write an adapter against the adapter API, first of all, you need to implement the adapter factory. This is what you provide to the StreamInsight engine, and the engine then decides when to call the factory, and by the factory, when to instantiate the actual adapter. So all you need to do when you implement this interface is override or implement the create method. The create method is supposed to yield an instance of an adapter. So in this case, that's the simplest possible implementation would be just to instantiate it directly and return that object. Now, what is my adapter here? That's the second part that you need to implement. That's subclassing one of our adapter classes that's provided by the StreamInsight API. In this case, it's a typed point input adapter with a specific payload that's known at design time. That's a struct or a class representing my event payload. And again, what you need to do here is just override the start and resume methods. The engine will call these methods when it's ready to receive events. So you are supposed to enqueue the events in those methods. The engine will provide a thread. So this is when the adapter thread is started and is supposed to start enqueuing events. Let's have a look at the code. Okay, so my factory, in this power meter case, all it does is for point events, creating an instance of my WhatsApp. This device is called WhatsApp, by the way. And this is why we call the adapter WhatsApp point adapter, and we return that object. So having a look at the adapter itself, it's indeed a typed point input adapter against the power reading structure. I do something in my constructor here to initialize the adapter, and eventually in resume and start, I do nothing else than just calling a method that enqueues my events. This is event loop in this case. Now what event loop does is, again, it's a very simple example. It has an infinite loop that enqueues events as fast as possible. This works for a single adapter with a single thread. However, this will not scale up, so this is probably not the best model for performant adapter implementation, but it serves well for demonstration purposes. What I do in my infinite loop is just checking whether the adapter is supposed to stop. This is something that the engine sets. If not, then the adapter will interface my serial port through the USB here, generate my power reading event from whatever it received from the device. And at some point, it will ask the StreamInsight engine to reserve a piece of memory. We have native memory management in StreamInsight, so I need to ask for a piece of memory here. Now I have my event. I can set the start time of the event, the timestamp. I can set the data, the payload of the event, and all I need to do now is to enqueue the event into the engine. And this is all the method does. Basically enqueuing as fast as possible. This is all the input adapter needs to do. Whenever it gets instantiated, it will start producing events. Okay. Now, talking about enqueuing events, there are interesting questions regarding the liveliness and the temporal order of events. In a very simple case, everything is in order, and my events, I can directly apply let's say, a windowed operation on my events. I know at each point in time the current status, and I will never get any late events. Let's say it's the simplest case will not create any problems regarding the computation of those windows. In this case, I have an overlapping window. Each window generates one result. And I know at each time if my window is already complete or not. Now, what happens if I receive a late event? If I receive an event, if the input adapter enqueues an event with a timestamp earlier than previously received events, let's say somewhere here, what does that mean for the two affected windows? Apparently, the result is not correct anymore. So the engine is supposed to correct those results. Now, how long can I go back with late events? What is the semantics for those late events regarding already computed outputs of Windows? and how long is the engine supposed to block results until it knows that nothing will change anymore. So we need some way for the input source to specify to the engine that things have been completed, things will not change anymore, versus things can still change. And to accommodate for that, we have a special kind of event which we call CTI, which stands for current time increment, which is basically a punctuation event that has a single timestamp, is enqueued by the event source, by the input adapter, into the engine, and tells the engine that everything before the timestamp will not change anymore. So everything that is based on windows, on aggregations, can be flushed from the engine and can be output to the output adapter. So let's see this in this example. I can specify the issuing of CTIs with two parameters. I can say after how many events are such CTIs to be issued by the adapter, and I can specify with what delay is the CTI to be issued. In this case, I say I want to issue such a CTI event every 3 events with a certain delay. So in this case, the delay goes back from the last received event, say X time units back, which enables me to create this grace period of the possibility of still inserting late events in that period. Again, I get 3 events, and I issue after 3 events the CTI with that certain delay from the youngest event. Now you see, that is already after the first window in my diagram here. That means that this first window cannot change anymore because this CTI specified that everything before its timestamp is done. So that will be output. Whereas the result of the second window is not done yet because there is still a potential of change in that period. So my event processing goes on, my CTI issuing goes on, and now the second window is closed and I can output something here. Now, this means that after the youngest CTI, things can still change and be inserted. A late event like this is still fine because it's issued after the CTI. So it's just a regular event. Whereas if the input adapter would enqueue an event here before the last CTI, this cannot be streamed into the engine because it would violate the semantics. Now, again, as a user, I have possibilities to specify a policy what to do with those events if they arrive through the adapter. I can tell the adapter either to drop the event altogether, if I prefer correctness, temporal correctness, over data correctness, and I don't care about the data of this event. But I can also specify to adjust the event to make it current, to move it after the CTI to ensure that it's temporally consistent, and I need the data. So I will change the timestamp, but I will keep the data. Okay. So at this point, I'd like to hand over to Basim, who will talk a little bit more about the underlying architecture.
Thank you, Roman. This is just to go over the stages of application development with StreamInsight. Roman already gone over this, but let's recap it. The first thing we do is we open Visual Studio, and we need a data source. So we need to have an adapter. Adapter could be provided by somebody else. Maybe somebody has already written a OPC adapter or a stock ticker adapter. Maybe it's from Bloomberg, maybe from Reuters, or somebody written an adapter for click streams from weblogs, etc. Either somebody gives you an adapter or you develop it yourself. As Roman mentioned, by the way, for the IObservable adapter, if you have anything that is IOnumerable, which means any link query at all, then you have automatically way to get it into StreamInsight as well. Once you have an adapter, both input and output, now you know the types of your schemas, what kind of events that you have. You can actually open up your Visual Studio, start a main program, and create a stream from this adapter for this type, and develop your application using LINQ. At the end, once you are done with your query, using the object model APIs, you compile the query, which triggers for us to execute our LINQ provider, which looks at the link query. And we have our own intermediate stream algebra and a language corresponding to that. So we take the link expressions and convert it back to this our native algebra, which is public and documented. And once the user wants to execute the query, then the engine compilation kicks in, and we generate a query graph and execute that query graph. Again?
No, it's the other
I'm sorry, the other way. Reiterate the steps. We open up Visual Studio, get the adapters, write the link query. Using the object model APIs, we register, compile the query. And at the end, we run the query. Here's the basic architecture of our product. Set intermediate language comes to compilation. We check the syntax with the parser. With the algebraizer, we derive the types, and we derive stream properties, whether stream is ordered, whether stream has retractions. As Roman mentioned, we have a very forgiving algebra in that events do not have to necessarily come in order. And till you give this punctuation, CTI, you can actually change your mind about the things that you told us. We will speculate depending on your settings. There's a wide range. We could tell you things as soon as we know, which means with the understanding that we can change our mind about it. On the other end, we can tell you things only we know for sure that they are the truth. So there's a wide range of speculation. OK, we derive the types. Then we go to compiler. StreamInsight algebra is based on relational algebra with some streaming extensions. So in the compilation phase, we are going to apply some of the optimizations and tricks we learned over the 25, 30 years of relational algebra history. We are going to push down the predicates. We are going to push down the projects. We are going to do global local aggregation and other tricks that we learned from relational algebra. We have our own metadata service, and this metadata can be either stored or it can be in memory. Our expression service uses this type system of the CLR, and expression service semantics are equivalent to link expression semantics. Once we compile the query, we'll have a runtime execution graph, and it is going to get executed. We have an operating system abstraction, which allows us to deploy our product in very different environments. For desktops, servers, we will be using SQL OS operating system abstraction, but we will be running in devices, in phone-sized devices as well, which SQL Server currently doesn't have an abstraction. So for those kind of environments, we implement our own. Again, we went over the development process. What does it take to develop a StreamInsight application? There was Visual Studio, which is great and all, right? You have seen how Roman was able to use IntelliSense to type his query. But strictly speaking, we started with the algebra. You don't need Visual Studio to write a query at all. If you were XML crazy enough, you could open your Notepad or VI or Emacs and write your query in XML. So we have our own intermediary language. If you were so inclined, you could write another front end, another syntactic surface to our product, such as StreamSQL or CSQL kind of thing. Another nice thing about our compilation is it's strongly typed, so we have type safety. We leverage CLR for many aspects. In a low latency streaming kind of environment, we really cannot afford to interpret expressions, so we widget them. Also, using Visual Studio tools and libraries makes our developing tools much easier. And again, as I mentioned, having CLR, using certain aspects of CLR makes it easy to port our application. For example, if Silverlight writes somewhere, there's no reason why we couldn't run on the same platform. Events. So CLR is great and all, right? It has all these nice aspects to it. You know, we get link expressions, we get jitting, we are able to port our platform into different form factors, and it has this nice garbage collected memory, except that, you know, we need to be able to give SLA guarantees to our customers, we need to be very low latency, and garbage collection could be a problem for those kind of scenarios. So we do not use garbage collected memory for our events. We have our own event format, more or less similar to SQL Server native event format, because most of our team came from original SQL Server engine. And your expressions are link expressions, though. So what we do is, whenever you refer to a column in the link expression, we actually JIT that code to go to the native memory and instantiate it for the particular expression that you have in mind. Again, Event Manager, there is some managed code there, but it's some infrastructure code, not the data code. We have a scheduler of our own. We have a data flow architecture. You know, every operator is independent of each other. They don't know or care what kind of query they are running, and they are composable. Every operator takes one or more streams and outputs one or more streams. This makes it very easy to compose queries or distribute queries over cluster-like environments. I'm sorry. Again, our operators are, they perform all those different operators, join, select, top K, union. The aggregate operators, they do incremental evaluation. We have one very nice operator, group and apply. It is somewhat similar to relational SQL group and apply, except that rather than running a single aggregate in the group, under the group, we are able to run entire subqueries within the grouping, which allows us to do, you know, scenarios like map reduce very easily, very naturally. You write 2-3 lines of code, and you are able to do map reduce in a streaming fashion. Currently, we are working on the clustering one. V1 will not have the clustering option, but we are able to utilize all the processors that you can throw us very efficiently, because multiple groups means multiple independent running operators. Okay, so we have all these nice operators, right? You have join, you have union, you have select, you have filter, you have windowing operators. What else could you want? You know, this is expressive, not quite Turing complete, but still quite expressive, right? But it's highly likely that we could not possibly anticipate all the domain-specific operations that you might want to do. So for this, we have extensibility. You can write user-defined static functions, UDFs. You can write user-defined aggregates, and you can define write user-defined operators. Are we going to push?
Yeah, let's show an example of a user-defined aggregate at this point, switching to the code. A very common aggregation in manufacturing as well as financial verticals is time-weighted aggregation, specifically time-weighted average, where I need to take into account what time period did my events occupy within a window of time. So I have a time-sensitive aggregation here. And to this end, we have a couple of interfaces for user-defined functionality. One of them is the time-sensitive aggregate operation. So in order to implement something like a time-sensitive aggregation, what you do is define a class that derives from our CP time-sensitive aggregate class. And in this class, all you need to do is override the method generate output. So what generate output receives is the whole set of events of a specific window. This is given here as an IEnumerable of events. That's what I receive. And I also receive the window itself, the window descriptor, in terms of start and end time of the window, so that I can relate the temporal properties of the events with the whole window size. And in this case, you see that a time-weighted average is basically 4 or 5 lines of code. I loop through all events in my window that I received at the runtime here. What I do is I take this, in this case, it's a column called payload. I take this column payload and I multiply that by the difference between the events end time and start time, which basically means that I'm weighing the events according to their time periods. And after this summation over all events, I divide the result by the whole window time. This gives me a time-weighted average within a couple of lines. This is still procedural.NET code, but it's on the other hand, it's a declarative way of defining an aggregation, because you do not need to worry, when am I called here? What is the sequence of windows? What is the sequence of events? It's declarative in the sense that I'm called with a window full of events. And at any time, I can specify the correct result based on that input. And that's all I need to do when I implement that aggregation. The engine will then take care of when is this actually called, when is this output produced, and when is it streamed to the next operator. Now, in order for me as a link author to use that as an extension method in link, I, as a UDA writer, author, can also decide to provide this extension method, just to enable the user of this aggregation to have the nice link surface again, and specify this aggregation just the same way we have our built-in aggregations defined on top of Windows. So in this case, I define an extension method, call it TWA. All I need to do is provide an attribute that connects the actual implementation with that extension method, so that our link provider then knows what to do if a user specified this extension method, and inserts that operator into the runtime query tree. This is never called. It's just used to build the link expression tree, of course. So this is basically, within this screen, you see everything you would need to implement for a time-weighted average. Okay. So let's move ahead. As a last thing, I would like to talk a little bit about supportability. The StreamInsight engine has a diagnostic interface, which enables you to retrieve statistical information at runtime about queries, about operators, about memory consumption, latency, and so on. This is part of the Object Model API. So within your application, you can interface the server object and retrieve that information through the appropriate methods on the server. You can also manage a StreamInsight engine, a running StreamInsight application through PowerShell. As long as this server exposes its manageability web service, you can interface that web service and use PowerShell to manage that on a script level. You do not need to go into Visual Studio to do everything management related. And last but not least, we have a very nice debugger tool, which enables you to gain insight into running StreamInsight queries, or enables you to record and replay queries. So let me show that by example of the query that we used before. So I'm still using that correlation query with the trend calculation. Let's run that. Okay. Now this is the debugger tool. It's part of our release. If you install our MSI, you not only get a bunch of DLLs I was talking about, you also get one executable that shows up in the start menu. This is the debugger. So the first thing I want to do is I want to connect to my running application. And if we have another look at the code of my application here, you see that before I start the query, I expose the management service. Programmatically here within those two lines, we expose a management service based on the server. I can get to the server from the query here. and I expose this as a web service endpoint with a specific address. So let me just take this address. This host is now open. Go to the debugger and say connect to a server on my same machine here. Now what I see in the Object Explorer, if it works, is what the diagnostic interface exposes to me through that web service interface. For instance, I can have a look at the query operators they're currently running. So what I did is I took a snapshot when I connected to the server, and I can now look into, say, my join operator and see the current memory consumption of my join. Join is stateful. It needs to maintain both sides of the join because of the possibility of events arriving later and still joining to the other side. So join maintains state naturally. So it occupies memory. I can see how much event memory it occupies, how much index memory. I can see how many times the operator was scheduled. I can go to the query level and look at the diagnostics here. I see the total memory occupied by the query. I see the number of incoming, outgoing events. I see the total latency, so I can calculate the latency per event, basically. So all that diagnostic information is captured and exposed to that interface. Now, what is interesting is if I have a look at the runtime query, what that gives me is the execution tree of that query that I specified through link. This is how it looks like from the viewpoint of the engine. I have an input stream created by the input adapter. At some point, I had this multicast, which was implicit in link. I just used the input stream twice. That created a multicast going into this, what I called slow aggregate and fast aggregate. On both sides here, then I have my temporal adjustments to make sure that the overlaps disappear. Eventually, I have a join, and this is what I output. So what you can do now is we can start recording a sequence of events. We do that now. Let's do something with the eCPU to have some interesting behavior. Stop that again. And now I stop the recording. So what I created now is, if I open that, I have a pretty long event type on the input side. So many fields that come from the meter. What I did is I recorded a sequence of events. You see a sequence here with their timestamps. Over that period, I recorded the events as they were flowing through the engine, and now I can apply some interesting insights and diagnostics to that recording. So let's see. I can, for instance, go to my, well, let's have a look at the input here on the level of the multicast. I can zoom out. Let's see whether this is still visible for you. It's pretty small, but at least I have the whole window here. I go to some point in time. Let's say I pick one event, and now I say I want to do an event propagation analysis. I want to see how did this specific event travel through my query? What did it cause on the output side in the join? I do that. And now the debugger tool will remove all the events from that display and leave only those that are related to my input event. So in this case, what I see is, for instance, in the aggregation case, let me close this again. So this was the aggregate for the slow window. It was the bigger one. And naturally, this input event contributed to more events on this level and less events on the fast window, because the fast window was only 1 second long. So this event contributed to 5 aggregation results, naturally, because I had 200 milliseconds shift. So this fell into 5 windows, basically. I shifted with 1/5 of a second. Whereas for 3 seconds, I have many more events here. For some reason, I can't scroll. I think I have to go back to the, yes. So here I have, must be 15, I guess, 3 seconds worth of events. And then I see how my lifetimes were changed, my event temporal characteristics were changed, and how my join was put together based on that input set. I can do a different analysis. I can go to the result. I guess we can stop that now here. We can go to the final result and see how how was this event created in my result set? I can do a root cause analysis. Now this goes back from this event and shows me all the events on the input side that contributed to this one, all the aggregations that contributed to it before it was joined. So I can gain some insight into the actual event processing at runtime and investigate why did I see something in the output, why did I not see something in the output, down to the operator level. Of course, it's tricky to do that in real time. If you have event data rates of hundreds of thousands per second or 50,000 or more per second, there's no way you can do that in real time. So what we have here is the closest that we can get to a debugging of a real-time event stream. What I can also do is can set a breakpoint on conditions. So say I have my output with my trend here. I can say set a breakpoint with a condition of the trend being greater than 0.8, for instance. And now I can say run until this breakpoint was met during my replay. So this gives me the first event that triggered that breakpoint. Apparently it was the first event that I got at all. And now I can go from there and see what happened at that point in time. What I also can do is just take the full set of replay events and step through that in time. Just follow the event sequence step by step from a certain point in time or from the beginning of the replay. And I see how the scheduler of StreamInsight was distributing CPU time to the operators and how the event was traveling through the tree. Okay. That's that. You've seen that. Okay, so what did we see? We were diving into the CP platform, the API. You've seen the code of the adapter, the queries, extensibility. What we have is an event-triggered framework, fast computation, event-triggered computation of real-time queries. We have an API for adapters, writing queries in LINQ, writing whole applications with different model, observable model, implicit server model, explicit server model with total control over the diagnostic interface, declarative link to specify queries without having to take care of temporal sequences of events, defining your query logic in a declarative way. We have a flexible adapter API that allows you to control the liveliness of the stream in terms of those punctuation events. How long do I want to wait for the output? How long can I afford to wait? And how accurate is my result supposed to be in terms of liveliness? It's extensible through the extensibility framework, user-defined functions, operators, aggregates, and we have a rich tool set of supportability, interfaces, and the debugger tool, of course. So I'd like to remind you to evaluate the session. You already know that PDC will donate $1 for each of you who writes an evaluation to some local charity. So it's not only beneficial for us. Please do that. And that's it. Any questions? There are mics, both sides.
How is it going to be licensed?
It will be licensed together with SQL Server. So we always stress that this is technically independent of SQL Server, but we are still part of the business unit. We are still a team within SQL Server. And this thing will be part of the SQL release cycle. We are currently still in our pre-release. That's actually something that I wanted to show you. If you, I don't have a nice small link, but if you search for StreamInsight November CTP, in Bing, of course, the first thing you get is our download site for the current beta release, which is the November CTP that is in sync with SQL Server's November CTP. That means we will ship together with SQL Server 2008 R2 somewhere in beginning of next year, first half of next year. So StreamInsight will be part of SQL Server release. There will be different SKUs according to the SQL Server SKUs. So they will differentiate by performance. That's not completely spec'd out yet, but it's going to be part of SQL Server.
Yeah, I got kind of like one question, but kind of divided into three. But all have to do with the
kind of like hosting. You mentioned that StreamOS thing where you leverage the CLR. So I guess that is what the engine is physically. So when I'm hosting the Insight engine in my own process, I host your StreamOS, which is kind of like a hybrid. Is that what it is?
Yeah, that's a good point. Currently, you'll get our own abstraction, our own scheduling, our own locking primitives, our own buffer management. It gets tricky when you are hosting this, when we are being hosted, rather than there is an executable where there's a service, StreamInsight.exe.
Yes, we also provide a very basic executable that just hosts the engine and exposes the manageability interface the same way I showed in my example, which just starts the server so that any client application can then, instead of doing that in process, connect to that server, register and instantiate queries, query templates, adapters, and run that in that server process.
Yeah,
so it's similar to an NT service, but it's not an NT service.
So for this case, it makes sense for us to either host CLR or use our stream host. But in the hosted case, we are potentially just one of the things that is being hosted, right? Maybe you are doing some stream processing, you are loading other DLLs. So it's not clear that it is us who should be hosting the CLR inside. So we don't have this for the host, for this case yet, but we are looking at in the future having this optional, host specifying, yes, StreamInsight, you shall host the CLR, or you are going to use SQL OS kind of thing.
Yep.
We don't have this for V1 so far.
Yeah, but it's not, actually it's not what I meant. When I want to, this morning, your colleagues, he demonstrated the kind of like the mechanics that StreamInsight needs to be hosted somewhere. I mean, where would that be? You hosted that in a console app.
Right,
Yes,
so we have our own host aside from that. Or you could write your own console.exe, just does what Roman just did in the program.
So, and then you just pull into an assembly, and then it's all encapsulated, and then the StreamInsight hybrid does its magic in that physical OS process? That's what you're saying?
Exactly. You just start the server, and we create our scheduler. By default, we are going to create a scheduler per thread, and those are all configurable.
Okay, and so the last question, but the same direction is, also mentioned this morning was the ability in a future version to host that in a Windows CE environment.
Yes, we are actively looking at this.
Yeah, and since Windows CE is a real-time operating system, what kind of events will you be capable of processing in a real-time, hard real-time time frame? I mean, such as manufacturing, industrial, plant kind of scenarios.
For the future. So you understand this is all speculation, right? I can't guarantee anything. We have certain scheduling policies. Currently, every time scheduler, those are all internal implementation details, mind you, but it can change. You can take a dependency on it. The way we look at Stream is, okay, somebody runs, they get a certain quota, and multiple ones could be running by default as many CPUs as there are. And after it's done, we are going to look at all the queues and choose the operator that's being fed from the events that has the oldest event. That speaks for lowest latency. We are trying to push the oldest event into the stream. In the future, we are looking at specifying SLAs, QOs, and triggering the scheduling. Since we have control over which operator gets scheduled, we would try to meet these SLAs and schedule accordingly.
My guess is you would not rely on compact CLR in that case.
I suspect CLR, by the time we do this, there will be an evolution of CLR and platform changes and stuff that I cannot speculate right now. We would be using them.
Just a follow-up question on the hosting.
Yeah.
What's to stop me from hosting this in Azure Compute? Are you going to stop me?
I'm sorry?
Of hosting the engine inside Azure Compute?
Inside? I did not.
Inside Azure. Windows Azure.
Oh, okay. I see.
Nothing.
Really? Okay, great. I thought you were going to say, no, you won't be able to do that because we're going to take that feature away and only make it work on premise in SQL Server.
No, I mean, as Roman mentioned, there are some licensing mechanisms. They are tied to SQL Server SKUs. You know, there's enterprise data center, and I suspect there will be a mechanism to enforce such capabilities commensurate with the SKU you are
Where you host
getting.
it, that's up to you.
But yeah.
All right, great, thank you.
There's a question.
Yeah, hi. Are there ways of expressing matching of sequential patterns on a single stream, A followed by B and not C, that kind of thing?
Yes, very good question. You can, if those simple patterns, A followed by B within a specific period of time, this is relatively simple to express with a join. You can take your stream, multicast that. On one side of the multicast, you shift the event with exactly that time period into the future or the past, and then you do kind of a self-join. Okay. And then you see whether an event A was followed by an event B with the appropriate join condition through that temporal operation. So if it is as simple as A followed B within X time units, you can do that with two operators, a temporal change and a join. However, if you're looking at something more generic, something that is similar to maybe regular expressions, where you are able to specify an arbitrary sequence of events together with the temporal properties, we do not have any specific language surface for that. However, actually, I just opened that part of the samples. These are the samples that we ship together with our release, so they get laid down by the MSI into program files as a zip file. One of the samples that we have here is showing how to do a pattern matching functionality. So this is the pattern detector. What this application does is it implements a user-defined operator on top of our extensibility framework, which applies a state machine functionality to that user-defined operator and lets you specify a pattern in terms of a state machine. Now, this is not as trivial as a one-line regular expression, but still it's a declarative way to specify a complex pattern that you could not express with a simple join or the out-of-the-box query operators. So this is one of the samples that we have. In this particular case, you specify your pattern here with transitions and vertices of a state machine. In this case, it's detecting in a stream of stock ticks whether I had n downticks followed by the exact number of upticks. So it's a pattern that is not trivial, but that is pretty straightforward to express with a state machine. And this example shows how to do that.
So we currently do not have a pattern operation per se, but there's a sample that shows it, how to do it according to your custom requirements.
Yes, so the query in this sample is just applying the window that I want to use for my pattern detection here. Within that window, it will detect the patterns. And then it applies that augmented transition network type of implementation of the pattern detector, which is, in this case, this is a user-defined operator that we implemented as part of the samples. So it becomes an operator as part of our extensibility framework, but it's not an operator out of the box. It's still just the sample code.
Okay, but, so maybe a follow-up then. Is there a way then of doing something like finding the first event that matches a pattern within a time frame? So let's say in a stock trader, I'd want to be able to say the first trade for the day on a certain stock.
Yep. It is this pattern operator followed by a type K.
Okay.
Yes, yes. So the way this is specified is very generic. Anything that you can express in a state diagram becomes feasible through that mechanism.
Thinking about that problem, I'm imagining an outer join scenario where I want to say I'm joining two groups and I want to kick out something even if there's no group so that I can feed back the group. But maybe I don't need an outer join.
There is a way to check for non-existing. In addition to join, we have a left anti-semi-join.
Okay. is that an outer join essentially? Like
Yes,
you
it's,
say,
it's,
and
it's just
not
another
in the
join
window?
kind. I'm
Well,
sorry.
it's an outer join with anti on one side. So it's triggering when you have nothing to join on one side with the other side. That's the anti in the left anti-semi join.
Is there a way to express that in LINQ? Because I tried to do an outer join syntax with the CTP and it didn't.
We
Outer-
have just CTP3 does have.
We don't have a
CTP3
native
doesn't
outer
have it.
join in our CTP3.
Right.
That is correct.
It's
yes.
going to be in RTM, sorry. It did not
Yes,
make
yes.
the
It's
CTP3.
It's provided for by the intermediate stream processing language. It's not surfaced
Right.
in LINQ
So
yet.
if we drop down and tried it in XML, as you say, we could probably get that.
Yes,
to work.
if you are crazy, I'm sorry, if you are an XML loving person. And, you know, as I mentioned before, when we start developing, we started with the algebra, right? It was the engine, you know, we started with the engine and we didn't have a language, you know, we had to write in XML and it's unbelievable how nicer, easier, you know, friendly it is having a Visual Studio, C#, LINQ kind of environment to be able to do those things because, you know, XML, as fun as it is, it takes a lot of time and effort.
Right, thank you.
Yes, sir.
Yeah, why don't you offer any, let's say, number of events window?
We do have,
The question was, why don't we offer count windows? That's what you're asking for, right? Windows that are not specified or not defined by a window, a temporal size, but by a number of events. We are currently working on that. This is, again, we should be careful making any assertions, but it's most likely to be in our V1.
Equals to an average?
Yes,
Yeah.
yes. Yeah, it's a crucial windowing operation, and it's on top of our priority list right now.
So you mentioned earlier that you have this, like you're building on so many years of optimizing relational algebra, you have this nice compiler and everything. And then I see this extensibility model, but I don't see anything like to express hints that you could use for
Right.
that to be optimized. And how does like pure.NET code work on your not a garbage collector managed
yeah, that's a good point. As things currently are, the user-defined entities become a barrier in the execution graph for our optimization purposes.
Okay.
We cannot cross them.
So that's basically right now for us a warning, like when we have very high throughputs, to be careful where and what we do with extensibility, right?
Of course, yeah.
I think the debugger execution graph reflects the actual execution graph to a high fidelity. That might be a clue maybe to such problems.
But you're right. Whenever you use the extensibility framework, then it's basically up to you what you do there. If you write a UDF that you use in a project expression, that will be called for every event. If you do something there which takes a lot of time, then you will naturally reduce the possible event rate. So that's the trade-off. By extending our out-of-the-box operators with user-defined things, you will affect the performance.
Unless we decide that it's a runtime constant, we'll fold it into a constant.
Right.
Then
To some
we'll only
extent, we can optimize, but at some point, you take over the execution.
So do you guys support not using LINQ when we go at the XML? So we write our own expression builder or call it compile down the algorithm?
So the question was whether we support also the direct XML interface to specify queries. And this is actually a publicly documented language. So if you go to schemas, Microsoft.com, complex event processing, I don't think I have a network connection, actually.
In fact, some of our ISVs expressed interest in targeting this. They have their own language existing, and they take this language and emit XML directly.
Yeah, it's there. At that URI, you find the complete the XSD, the XML schema of our intermediate stream language, all the operators, how they are defined, and then you will see how this maps to LINQ and how the engine processes that. So you can go directly against that interface as well in the explicit model, explicit server model, where you have total control of how you interface the engine. At some point you say, create query template. Let me see. So there is an interface here. You see that also takes an XML reader. So you can specify a query not only link and use that to create the query template, which is our metadata object for the query logic. You can specify an XML reader based on an XML query template and completely bypass link.
So
So as an ISV, then my end customer would have to use my SQL server and then their license?
That depends how you handle that. As
yeah, we don't want to speculate
yes.
about the exact details
There
of the
might be
licensing.
an alternative for ISVs, but I can't really give you any specifics about that. But there is an ISV channel for that as well. If you want, we can follow up with that, and I can direct you to the appropriate persons in marketing, licensing.
Again, those are all niceties, right? Strictly speaking, as long as you have a management service exposed, you are listening on some web services endpoint, you can speak SOAP. We don't even have to use the object model APIs.
Yeah.
But, we built object model on top of the SOAP and makes it easier.
Yes.
Is there a way to use XML to express the type metadata as well?
The question was whether you can also specify the types, not only the query templates in XML. So that's a good question. Internally, we also use XML for that. Now, as far as I'm informed, we don't have an interface. We don't expose that possibility to submit that.
Yeah, we talked about that, but I don't think. Yeah,
you can bypass link, but you still use you still use .NET to specify your other pieces of metadata. Use structs or classes.
There is still an escape there, though. You don't have to use the object model.
Right.
You can use SOAP APIs, web services.
You can host a server, expose its metadata interface, and then use a separate client that talks the SOAP protocol. And that could be a Java client on Linux, anything that understands and can talk SOAP. Because eventually that's what it is. That's how you talk to a remote server, is SOAP.
So you could use dynamic as well,
Dynamic
dynamic objects.
objects?
Could you use dynamic
Oh.
objects as an event?
Well, the question is whether we can use dynamic objects as events. Now, our streams are strongly typed. As soon as you instantiate a stream, a query, all the events in that stream need to follow the same structure, the same type, our own event type. So that's static at runtime.
Yeah, I mean.
Yeah, an interface rather than
You could presumably simulate something like that by modeling everything as a blob and having static function calls, get field, get property, get property, get property. But we do not have a built-in way currently. Yesterday Eric Meyer was talking about such a link way of doing things. Our type system is basic CLR types currently. For V1, we do not support composite types. But in a future scenario, you could imagine a case. Currently, we take CP stream of T. One could take CP stream of iData reader of T. And iData reader, as you know, has things, get int of one, get string one, column number, and those kind of things. So this will be totally dynamic, just as iData reader is, but we do not have it currently. If you are so inclined, you can model the whole thing as everything is a one big byte array kind of thing, and use static function calls that retrieves a particular field from that serialized byte array that you have.
Any other questions? Well, thanks again for being here.
Thanks for staying for the last hour of the conference. Thank you.